that's how we're going to start out here tonight. We're going to learn and we're going to have some fun with this. But before we go any further, let me say this to you. I noticed that in these classes, and this is actually like the 4th class now that we've been teaching this year, on the basics. We were asked by contractors to put on a class on the basics. I says, why do we want to put a class on the basics? These are supposed to be people who already know air conditioning. They asked us to put on the class, and so we tried it. And I cannot believe the quantity of people. I've not had less than 20 people at a class. And we've got somewhere like, 35 have signed up. So here tonight, we're close to 30. I also found out this, that if you are currently in a trade school, and you come here to get another version of this material, you're in the right class here tonight. If you have been in air conditioning for a while, and know pretty much the business, you're also in the right class. Because this is your refresher on all the things that we learned but forgot. And I will teach you how to use some of those things. So what I'm going to, so I guess what I'm trying to say is that for whatever reason you are here tonight, you're in the right class. Okay? All right, so let's go now. This happens to be what? That's a question for you. And I guess I'm asking you the question for those of you who know refrigeration at this point, because if you don't know, you won't know what it is. And by the way, my lecture tonight is based on the fact as if you knew nothing about this business. If you know absolutely zero, so that's exactly how I'm lecturing to you tonight. So this is what? It's a basic refrigeration system. Right. Because it has, and don't write anything down now because I will be going through this part later. But that's a compressor, that's a condenser, and that's an evaporator, and we have refrigerant flow. So my question is, and what is it? And you say it's a basic refrigeration system. Well, what does that mean? And by the way, I teach like this. So you have to put up with me for 3 hours. I get excited in order to keep you and me awake. It's a basic refrigeration system, but what is it? What can that be?
Anything. It can be a refrigerator, it can be an air conditioner.
Absolutely. Excellent answer. And that's exactly what I was looking for. It could be the refrigerator in your kitchen. It could be an air conditioner, which means it could be a room air conditioner or it could be a central air conditioner. You see that? It can be this too. This is a refrigeration system that cools pop. All refrigeration systems have the same components. They all got compressors and they got coils. And they all work the same. You diagnose them the same way. It can also be a gigantic chiller that cools water to cool a building in the summertime. Basic refrigeration system. Okay, we're going to come back to that. I'd like you to turn over to the next page. We're going to run through some of this stuff. Some of it, again, you may know, and some of it you won't know. I will pause, I will stop, and by the way, I will stop and ask you if you have any questions or comments during the lecture. I have a tendency not to do that. And just so you know, with my notes, I wrote myself a note in order to stop and ask you that. But at any time, if I didn't ask you that, but at any time, if you have a question, you have to raise your hand and ask, okay? That's the only way that we get to know this business. Ladies and gentlemen, these are two thermometers. Look at this. This is Kelvin and Celsius, and we're not going to deal with that tonight because that's metric. So we come over here to the Fahrenheit and Rankine is used in engineering. So we're not going to use that tonight either. The only thermometer that we're going to be using, measure of temperature, will be the Fahrenheit thermometer. Is that clear? So when we talk about temperatures, it's strictly Fahrenheit. Let's read a little bit. It says, heat is a form of kinetic energy. The molecules in motion collide and give up energy that can be measured. The higher the temperature, the greater the molecular activity. Isn't that what we learned in high school? Isn't that really what we learned back in our science classes about molecules? Everything contains molecules and they're in motion, correct? This furnace has got molecules. What's your first name? Kurt. Because that's what I do tonight. I ask people their names and I pick on them and so forth. Kurt? Or Kurt? Kirk. Kurt? Kirk has got molecules, doesn't he? Kirk is made up of all kinds of molecules. And the point is the molecules in Kirk and the molecules on the furnace move around. And the first two sentences that we had here, the second one said, the higher the temperature, the greater the molecular activity. Isn't it true that the molecules in that furnace move around quicker when it's in a hot room, as opposed to us taking a furnace and sticking it outside? So if it's outside, it's colder, and the molecules slow down. This is important to know, because when Kurt goes outside, well, his molecules are the same, because we got body temperature and all that, right? But the point is, molecules move. Do we really need to know this stuff? You betcha. Because of this. It says, all substances contain heat. Scientists tell us that the measurement called absolute zero is the point at which all molecular activity stops. Watch. This point is minus 460 degrees Fahrenheit, and everything above this temperature retains some heat. So they're saying that molecules continually move. That creates heat. So if we have more heat, the molecules move faster. There's friction. But in theory, at minus 460, that's 460 degrees below zero, there's no heat available, because all of the molecular action stops. So here's a question for you. Is there any heat at minus 459? Yeah, not very much. Do we really need to know that? You betcha. Here's the reason. In refrigeration, there's one thing that you have to remember, and that is heat does move. Heat moves from what? Hot to what?
Cold.
To cold. It never goes into reverse. Heat moves from hot to cold. And what we're talking about just in the first few paragraphs is very important, that heat moves from hot to cold. What temperature is the food in your freezer at home about, if you know? Does anybody know? The food in your freezer is how much? What do you think?
20.
What's your first name? Bernard? Bernard is correct. When you buy frozen foods from the grocery store, it's minus 20. That's commercial refrigeration. So from the store, it's minus 20. The freezer in the store is minus 20. But in your refrigerator at home, your food is zero. That's residential refrigeration. But if heat moves from hot to cold, if your food is 0 degrees in a freezer, maybe when that food starts getting up to 2 and 3 degrees above zero, now the refrigerator turns on to cool it off. The coil is 20 below zero. In the store, the coil is 40 below zero. But in your home refrigerator, the coil that freezes your food is 20 below zero. Isn't 20 below zero colder than 2 above zero? So all the heat from 0 degree food moves to the 20 degree below zero coil, because heat moves from hot to cold. And you have to know that in air conditioning, because heat moves from hot to cold. When we're in a home and we're trying to cool it, don't we take a lot of hot air? And right here, this here would be an air conditioner in a home. If we take a lot of hot air and try and cool it, we have to run it through a coil that sits here, and the coil is cold. The coil's about 40 degrees, and maybe the air coming back to it is 100 degrees. So actually the air gives up the heat to the cold coil by running it through the coil, and that's how we cool the air. Is that really important? Yeah, because of this. It says there's no heat at minus 460. But there's plenty of heat above it. I'm leading you somewhere, so stay with me. Here we go. Something either feels hot or cold when it's substantially warmer or cooler than our body temperature. That's just how we feel, correct? What's your first name? This man right here. What's your first name?
Martin.
Martin? Martin, are you cold at 0 degrees?
Yeah.
And if you walked outside and if it was 0 and you took your coat off, would you be cold outside? Yeah. What about when it's 100? How would you feel then?
Hot.
Hot, right. And that's just how we feel. Is that important? Yeah. 0 is cold to us. 100 degrees is hot. But watch. Air, Martin said he was cold at 0. Air at 0 degrees still retains 89% of the heat that it contained at 100 degrees. Heat that can be measured with a thermometer is called sensible heat because we can sense it. The measured temperature does not indicate how much heat is present, but rather the intensity of the heat. Martin said he was cold at 0. So 0 is very cold to Martin. Because if Martin walks outside and it's 0 degrees, guess what? Heat moves from hot to cold. All of Martin's molecules that are making him nice and warm, all that heat is transferring to the cold air, correct? Because 0 degrees is colder than Martin. Heat moves from hot to cold. 0 degrees is very cold to Martin. But ladies and gentlemen, 0 degrees is not cold to a heat pump. And in this business, you have to understand heat pumps. We are seeing them in this area. We're seeing more and more of those, and you better understand it. Because what it's telling you here is that when the air is 0 degrees, it says it's got 89% of the heat that it had at 100 degrees. You take the same air that's 100 degrees and that's hot to Martin. You make it 0 degrees, that's cold to Martin, but it ain't cold to the heat pump because there's 89% of the heat left. Doesn't 0 degrees have a lot of heat? Yeah. Isn't 0 degrees a whole lot warmer than minus 460? It's a lot warmer than minus 460, and there's all kinds of molecular activity at 0 degrees. That's the point. So now, heat moves from hot to cold. We have a condenser. In fact, we got condensers right here. These are the coils that cool your house. We put those outside in the summertime. And when we start cooling the house, the air that comes out of there is very hot. But if we reverse the cycle, if we take the refrigeration system and reverse the cycle, now that coil becomes a heat pump. And in the wintertime, if we make that coil 20 below 0, just like the coil in your freezer, then the 0 degree air that's outside gives up a lot of heat to the 20 below 0 coil, because heat moves from hot to cold. And all the heat that this heat pump picks up, it pumps it back in to the inside coil, and now that inside coil is reversed and it's hot. We put heat inside the house. Am I making headway a little bit? The coil's 20 below, 0 degrees. Martin's cold, but the heat pump says, this is great, all this heat available. Let's pick it up and heat up the house. The basics of refrigeration. Heat moves from hot to cold. Okay? As insignificant as that may seem, the rest of what we do, it will fall into place. Let's go on to the next page. Isn't this great stuff, huh? Again, I'm leading you somewhere. Again, I'm basing this on the basics. This here, look at this. It says heat measurement. Heat can be measured in 2 specific ways. Heat intensity is measured with a thermometer. Look at that, heat intensity, see? Is measured with a thermometer and is commonly referred to as temperature. But the measurement can be made in either Fahrenheit or centigrade, and we're using Fahrenheit. So look at this. We got a thermometer, and we got a pound of water and some fire. Look at this, though, a pound of water. How much is a pound of water? I mean, if I say a pound of water, I don't know. What kind of quantity is a pound of water? How much do you think?
7.5 gallons.
How much? What? How many, figure out how many pounds in a gallon of water, right? Ladies and gentlemen, a pound of water is a pint. So like a pint of ice cream, it's a pint of water. So now if we take a thermometer and stick it into a pint of water, or a pound of water, and if I put some heat under it, all I'm saying here as the example is I had 63 degrees before and I warmed it up and it's 64 degrees. That's nice. But look at this, it says heat quantity. Heat quantity can be measured in British thermal units. So we call heat BTUs. It can be measured that way. It's a quantity of heat. Now listen up. When you take a CM exam, there's a question on there and it says, give us the definition of a BTU. Well, it's a quantity of heat. But the definition of a BTU is, and you don't have to memorize this because you're not taking a CM test, but the definition of a BTU is that it's a quantity of heat that will raise the temperature of a pound of water just 1 degree Fahrenheit. That's what the definition is. And there's all kinds of books out there. And if you turn the book and it says, I want to find out what a BTU is, and you turn over to that page and it says a BTU is the amount of heat that it takes to raise a pound of water 1 degree Fahrenheit. Okay, so what does that mean? Well, it's a quantity of heat. So when you answer that question right, they say, well, you know what a quantity of heat is then. You know what a BTU is. what a BTU is because you know what the definition is. Baloney. You know nothing by a definition because a lot of the books out there just simply say it's a quantity of heat that raises the temperature of a pound of water 1 degree Fahrenheit. And that means nothing to me. And there's only 2 places that I know of right now, so I won't tell you which one I copied this one from, but there's only 2 places that I know that really put it in everyday language. Because it says right here, 1 BTU is equal to heat produced by burning 1 wood kitchen match. It is also the amount of heat needed to raise a pound of water 1 degree Fahrenheit. Now that makes sense. If I take a wood kitchen match, 4-inch wood kitchen match, and if I burn it and consume it with no ash, now that's a quantity of heat that I can relate to. Hey, that's nice. So now if I take 1 wood kitchen match and stick it under the pint of water, I know that 1 match will raise this temperature 1 degree Fahrenheit. So it went from 63 to 64. But I have a question for you. I start out at 63. I put 5 wood kitchen matches under the pint of water and consume them. What temperature will that water be? 5 wood kitchen matches from 63, and it'll go up to 68. That's easy, isn't it? Oh, but except the definition is the BTU is the quantity of heat that'll raise the temperature of a pound of water 1 degree Fahrenheit. Blah. But I can understand the match. That makes sense. Now I have another question for you. Some of you here know what size input furnace you have at home. Who knows and would like to tell us? You have a furnace at home that has an input in gas and heat quantity. Who knows what they have?
75,000.
You do? What size is your furnace at home?
75,000.
75,000. What's your first name?
Scott.
Scott? Scott has got a furnace in his home that has an input in fire of 75,000 BTUs per hour. Now that makes sense. When Scott's furnace goes on, we got fire in there. How much fire? We got 75,000 BTUs, and that means nothing. But now, gee, that is the equivalent of burning 75,000 wood kitchen matches every hour that it burns and no ash left over. Now that makes sense. Now I can understand that. It's the same thing. If we say, well, gee, I'll sell you a 100,000 BTU furnace. Oh, that's a bigger quantity. More wood kitchen matches. But doesn't it make sense? Now watch this. Who has a central air conditioner at home and knows what size it is? You got a central?
2.5 ton.
You have a 2.5 ton? Scott, right?
Yeah.
Scott has also got a 2.5 ton central air conditioner. And when we did this the other night, somebody said, what's a ton? I said, okay, now I had to pick my brain. See, well, in refrigeration, first of all, it's 12,000 BTUs per ton. And what that means is it's a quantity of heat that will melt a ton of ice. That's all it means. And if you break it down through a 24-hour period, it's at 32 degrees, by the way, but it'll melt it from solid to liquid. And in a 24-hour period, it's per ton, 12,000 BTUs per ton. So Scott has got a 2.5 ton, so you would have then what, a 30,000 BTU air conditioner, correct? While Scott's air conditioner is running, and it could be one of these, there is a quantity of heat that is coming out. Because a refrigeration system is simply a pump that pumps heat. The gases pick up heat, and we put the heat somewhere where we don't care. So we have to refrigerate something. So when Scott's air conditioner is running, all the heat that you feel is 30,000 BTUs per hour while it's running. That it means it's removing from his house the equivalent of burning 30,000 wood kitchen matches with no ash left over per hour. Now I can relate to that too. 30,000 wood kitchen match worth of heat per hour. Now this makes sense to you? You now know what a furnace means in BTUs, and you know what an air conditioner means in BTUs. Even if you had a small window air conditioner, it could be an 8,000 BTU window air conditioner. The smallest one made is 4,000. 4,000 BTUs is for a small bathroom, really. And 8,000 would be for a small bedroom. But even if you had a 4,000 BTU air conditioner cooling a small room, it would be the equivalent of removing 4,000 wood kitchen matches per hour, quantity of heat. Okay? Okay. 1 calorie will raise the temperature of 1 gram of water 1 degree centigrade. Who cares? That's metric. And 1 BTU is equal to 252 calories. We don't have to worry about that. Let's go on. Next page. I want to get through the basics. So now we gave you some charts. It takes you a whole semester in refrigeration to get through these charts. So I give you these charts and we'll get through these in 5 minutes. But these charts you really do use in this business. Because look at this. We have, oh, by the way, when I teach a class, it's generally the person that is on my farthest to the left that I pick on. What is your name?
Annette.
Because you're the one that's farthest to my left in the front row, right? No, but it's in the front row. So Annette, you got a job here to do tonight. To keep everybody awake, I'm going to say, Annette, and you're going to pick on somebody. And you just turn right around and you say, okay, him. And then you turn around over here and you say him. And these are the people that will answer the questions, okay? But if you're not quick enough in that, guess who gets the question? You. So you got to be ready, and you got to say, okay, it's him, it's her, it's him, okay? And that's the way we do it, because as we go on here, and you have to get ready now, the charts are showing a substance. It shows you the density of material, of substances, and it shows you the specific gravity. So look at here, density is measured in pounds per cubic foot. So if you take a look at all of these substances, it says that if you had a cubic foot of them, it would actually weigh that much. And if that was true, then they would have a specific gravity, and it's a certain quantity, and we can compare things here. So let's say this person now is going to pick out any substance here, and we'll talk about that substance. So Annette? Him. Okay, him, right? Okay, good. Pick out a substance, and again, we're just going to do this. We're not going to worry about first names or anything, but it'll be him or her, whatever. A substance. Water. Water. Usually it takes us a while to get to water, but that's good, because water being first, everything else is easier now. Look at this. If we have a density of water at 62.4, that means a cubic foot of water is 62.4 pounds. That's how much the water weighs. But watch. That means specific gravity of water is 1. All the specific gravity means is that everything else that we exist with is compared to water. If water is 1, that means everything else is either lighter than water or heavier than water. Water has a specific gravity of 1. You see how much it weighs per cubic foot, correct? If that's true, are you ready, Annette? Yeah. If that's true, we're going to compare water with something else in here. So that something else in the substance would be, Annette? Her. Her, okay. What substance do we want to do?
Gold.
Gold. Look, oh, that's really good, right? Look at this, though. Gold weighs 1,204 pounds in a cubic foot, right? Look at this. Gold is 19.3. Is it 19.3 heavier than 1? Doesn't it have a specific gravity that is heavier than 1, that is more than 1? That means gold is heavier than water. That's all it means. Gold is heavier than water. You can see it by the chart. Another substance, Annette.
Not him.
Okay, right down the line. I love it.
Lithium.
Okay. Lithium. Whatever the heck lithium is, but lithium, look at this. It's only 33 pounds. Hey, you know, that's really a good example, though. Lithium has got a specific gravity of 0.5. It's less than water, isn't it? That's neat, if you knew what lithium was. Now, I don't, and I can't, but especially I can find out. Yeah, another one. Okay?
Ice.
57 density, point what? 0.92? Ice is lighter than water. But isn't ice water? Isn't ice water? Why is ice less than water?
Different stage.
Yes. You know, it's a solid. Water's a liquid. And all we know is that it's lighter than water. Do we really know that? Is ice lighter than water?
Sure.
How do you know?
Specific gravity.
Yeah, but how do you really know in the real world? How do you know that ice is lighter than water? It floats. How do you know that? Huh? How? And that's really good. I'm glad you're saying that. How can you envision ice and say, okay, I can always remember, I can't remember what the specific gravity was, but I know that ice is lighter than water because ice floats, and I can remember that because
When the temperature of water is equal to the ice will rise.
But how do you know that? Give me an example of how you know.
Take a thermometer and look at it.
No, it's a great
Stick some
example.
ice cubes in a glass
It's
of
what?
water.
Huh?
Stick some ice cubes in a glass of water.
Right, a glass of pop, glass of water. But what's even better than that? It's on the news all the time.
No.
Icebergs, right. Ice on the rivers. You see ice going down the river. Ice is on top. That's all. It's just a matter of remembering. Are you ready? Another substance, Annette. Okay. We got to mercury, ladies and gentlemen. Look at this one. You better remember mercury in this business, because mercury, look at this, 845 pounds per cubic foot. Mercury is 13.5. It's 13.5 times as heavy as water. You know why you got to remember that? Because, well, yeah, mercury is used in thermometers. But you see, ladies and gentlemen, we use water. Water's got a specific gravity of 1, and we use water in this business. Our instruments measure everything in a column of water. In other words, if we have pressures, we can have negative pressures that pull, we can have positive pressures that push, but everything is measured in inches of water column. Except that when we get to pressures that are too high, it would actually push a column of water too high, and we cannot make an instrument out of that. We can actually push a column of water. We're going to be talking about atmospheric pressure later. Atmospheric pressure can push a column of water like 3.5 stories high. It doesn't make any difference what the diameter of the column is. It could be that big, or it could be a big barrel 3.5 stories high, and it'll push it actually that high. So we can't make an instrument out of that, so we use mercury. And so now the instrument is 13.5 times smaller. It's still called inches of water, but yet we can also call it inches of mercury too. I'm only showing you that is because when we start using instruments in this business, you got to know why we use mercury and why we use water. Okay? So, the density then of water is 1. Let's jump down here to this chart, specific heat. Are you getting ready on that? Yeah. Take a look at this specific heat. Remember? It's a quantity of heat that will raise a pound of water 1 degree Fahrenheit. Look at this. Specific heat is how many BTUs it raises a pound of something 1 degree Fahrenheit. That's all this means. And of course, if everything is compared to water, look at what the specific heat of water is on this chart. Do you see that? The specific heat of water is 1, because it takes 1 BTU to raise a pound of water 1 degree Fahrenheit. So everything else is going to be less BTUs or more BTUs to raise a pound of it 1 degree Fahrenheit. So let's compare water to what? Annette?
Yeah.
Substance.
Seawater.
Seawater. Salty water, right? So the specific heat of seawater then is less than clear water, pure water, okay? So it's 0.9. Annette?
No.
Well, you're making it easy. I love it. That's great. Okay.
Ice.
Ice. There it is. See? The specific heat of ice then is 0.5. It only takes a half a BTU to raise a pound of ice 1 degree Fahrenheit. And it takes a whole BTU to raise a pound of water 1 degree Fahrenheit. We got to know that. However, just for the heck of it, take a look at, I love copper. Look at copper. What's the specific heat of copper?
0.092.
So what does that mean? 0.0, where's it at? 0.092. Isn't that 92 thousandths? Watch. It takes 1 whole wood kitchen match to raise a pound of water 1 degree Fahrenheit. It took a little less than a whole wood kitchen match to raise a pound of seawater 1 degree Fahrenheit. It took a half of a wood kitchen match to raise a pound of ice 1 degree Fahrenheit. But on copper, can you even visualize 92 thousandths of a wood kitchen match, a 4-inch wood kitchen match? Because that's about how big they are, 4 inches.
1/10.
Is it? 95.92 thousandths. Yeah, that'll be 1/10. It's like what? Would that be more than 1/8 of an inch or less than 1/8 of an inch? But if it's 4 inches, it'd be 4 times less than 1/8.
100.
Yeah, I guess you could see that though, couldn't you? It'd be small. So it might be what, 1/4 of an inch?
Yeah.
Something like that, because again, we're dealing with 4 times that amount. So you got, only because you got 4 inches. So the point is, if you got about 1/4 of an inch of a wood kitchen match, approximately, that'll raise a pound of copper, 1 degree Fahrenheit. Well, that's right. And the point is, it's a different kind of material. Copper is an excellent conductor. Water is a lousy conductor. Copper is an excellent conductor of heat and electricity. See, so now some of this makes sense. We use copper, we use aluminum, and we use steel in condensers and in evaporators. So that's insignificant, that's up to engineering to figure all that out. But the point is this, let's go over here now to the specific heat of these substances. Now the next person that you're going to ask in that, we're going to ask them a question, and that is, if they were to own a grocery store, what substance would they like to sell? So the next person that you're going to pick on is?
No.
Him. I love it. Okay, if you own the grocery store,
Yeah.
what substance would you like to refrigerate?
Beer.
Beer! That's great. Is it on here? But that's okay. What's the specific heat of beer? We don't know. But because you're owning a grocery store that doesn't sell alcoholic beverages, what product on this sheet would you like to refrigerate and sell to your customers?
Flour, yeah. 'cause
Flour?
we need to refrigerate.
Okay, so the specific heat of flour is 0.38 BTUs per pound of flour. It takes 0.38 BTUs to raise a pound of flour 1 degree Fahrenheit. But you see, if you owned a grocery store, and if you had a semi come in with a semi full of flour, see, what temperature is that flour coming in off of the semi? You know, could it be 50 degrees, or could it be 100 degrees? The point is, how many pounds of that flour will you want to refrigerate if that's what you do with flour? I don't know, but let's say you had to refrigerate it. Maybe you're in the grocery store bakery business, and maybe you have to cool that flour down to a certain temperature. Ladies and gentlemen, this comes in engineering, because if you are in fact putting it into a cooler, and coolers cool everything, but if you're putting it into the cooler, how much of a material are you putting in? How much reduction of temperature do you want to do? How many pounds of it? See, all of this are factored into the size. And all of this is the same reason why we size air conditioners, so they are also the proper size for our house. So we cannot take any of this for granted. This pop cooler is sized to cool X amount of cans, because there's a specific gravity of pop that would be just like beer, because we do have beer coolers too. But everything has got to be sized for whatever you're putting it in, but what temperature did you start at, and what temperature do you want it to go to? Heat. Heat moves from hot to cold. In the summertime, in Chicago, we have swimming pools. We heat the water because the swimming pool is too cool. If you lived in Arabia, where it's 120 degrees, you have a very hot swimming pool, and you want to remove the BTUs from the water and cool it down, and so we refrigerate water in Arabia. In Chicago, we heat swimming pools. In Arabia, we cool swimming pools. And I got news for you. In Phoenix, Arizona, we cool swimming pools, because we have 115 and 120 degrees in Phoenix. Okay, so it's the same thing. It's not here, but you have to know this business. Okay? All right, that's enough on the charts. Let's go on. Now I have my notes, because I have to stop now and ask you for questions. So at this point here, what's troubling you? This is not easy stuff, by the way, that I'm giving to you, and I'm giving it to you very quick. So questions and comments. What do you think? Are we okay so far? As we go on now, if you got a question on this, you have to stop. Okay, I want to go on though, because the next page says there's something that we do need to know about, and that's superheat. And we will get into this later, but it says it's heat added to a vapor. And it says superheated vapor is vapor which has had heat added to it, and it is now warmer than it was when it first became a vapor. It's just a definition. Don't worry about that now. We'll get into it later when we get into the refrigeration gases. But heat transfer. Heat is transferred in 3 ways. all, it says heat is energy. We already talked about that. Heat travels from warm to cooler, hot to cold. And there's three methods. You got to know the methods. By conduction, that means the molecular motion is transmitted to adjacent molecules. Convection, heated air or liquid is conveyed through pipes to another area. So look at that, liquid or air. And it says radiation. Now watch, you're going to learn something here. Behaves like light. Materials will either reflect, absorb, or let light pass through. And radiation transmits heat between any surfaces which are at different temperatures. So let's go to the next page and we see examples there. Because on the top, we have an example of conduction. Look, fire, steel rod, in our hand. By conduction, the molecules move the heat. So after a while, what happens? Yeah, burn your hand, right? Okay, but that's conduction, and at least now you can understand this. But look at this one, convection. Ladies and gentlemen, this could be your furnace at home. It could be a boiler because we said by convection is water moving, but this is a forced air furnace. Look at this. We could also put a coil in here. And that's the shape of a coil. It's in the shape of an A. We blow air through it in order to cool it off. But we could say now that if we have a fan in here, we're pulling air from a room and we're pushing the air into the room. These are the basics right now. Whether it's winter or summer, we have an unconditioned room that we want to condition. So that means we have to return unconditioned air. In the wintertime, it's going to be heated. In the summertime, it'll be cooled. So if we are returning unconditioned air, we will call these pipes, the ductwork, the return system. And then if we condition it to go back into the room, we have pipes that are supplying conditioned air. And we now call this the supply. This is the basics of terminology. And let me tell you why this is important. If you do not know the terminology, that's a problem in this business. I deal with a lot of cases, with a lot of people. I deal with lawyers, ladies and gentlemen, and these lawyers scare me half to death because I don't deal with lawyers very well. But contractors get themselves in trouble today when they don't know the business. Last year, I'll just give you a very quick example. Had a contractor call me about an air conditioner that we sold him, and he damned the product. He says, terrible, rotten air conditioner. It don't work. And it didn't take me 2 minutes into the conversation where I had to start asking him questions. He doesn't even know the terminology of the gauges. Knew nothing at all about the high side and the low side, which I'll show you in just a little bit. He didn't know the basics of terminology, which means he doesn't know the business. How can you fault the product when you can't service it or install it correctly? Terminology means a lot. That's the only way that you can talk intelligently. When you come in here to Park Supply and you ask our Park Supply counter people for some ductwork for the supply or for the return, they have to know what you're talking about as well. Terminology is important. Okay, anyhow, if this is the return and that's the supply, that fan motor is just like a vacuum cleaner. It's pulling and blowing air. It's pulling air out of the room and blowing conditioned air into the room. Now watch. If this here is a furnace and an air conditioner, if it's winter time, unconditioned cool air comes in here, goes through a heat exchanger because the heat exchanger picks up heat from the fire, and heat moves from hot to cold. The very hot heat exchanger gives up the BTUs to the cool air. That's how we heat the air. So the cool air is coming in, and the heat exchanger gives up the BTUs, and of course then we supply conditioned warm air to the room. But in the summertime, we return unconditioned hot and humid air, and we go through a coil that is 40 degrees, so if it's 90 degrees coming back, the coil is 40 degrees, the 90-degree air gives up the BTUs to the 40-degree coil. And then we supply cool air to the room. Is that clear? So, is this part of the air conditioner? conditioner. Can't we also call a furnace an air conditioner? All it does is condition the air. Okay? All right, but we call them furnaces, and that's the way it is. Ladies and gentlemen, watch. If this is like a vacuum cleaner, and we're moving air, if I drill a hole in my return, because it's pulling on the return, and if I take a piece of tissue paper and put it over the hole, does the piece of tissue paper get blown away or sucked in? Okay, and then we call that, because it's pulling and it gets sucked in, we call that negative pressure. And you have to know that, because when you hook up instruments, you have to put the negative hose in the return. Because if I do the same thing in a supply, drill a hole in the tissue paper, then would get blown away or sucked in? Get blown away. We call that positive pressure. The basics. Returns are negative, supplies are positive. Okay? Now, are you ready to learn? What's this? Radiation. It's like an electric heater, and we heat the hand, right? The air does not get hot. Who's got a thermometer in their pocket? Anybody got a pocket thermometer? Nobody got a pocket thermometer? We always got to carry a pocket thermometer. Even I don't have one. But in any event, let's say this was a thermometer. You ready? We want a nice hot summer day temperature. Annette? Nice hot summer day.
82.
82! Is 82 a hot summer day? That's a nice summer day.
That's a nice hot.
92. 92 is pretty uncomfortable and it's almost hot, right? But 92 degrees. Now, we would ask you to take the temperature, the ambient temperature. The word ambient means the surrounding air. So if he asked you to take the ambient temperature, you would pull out the thermometer. And we would say, just take the ambient temperature. And the sun is nice and bright. So we say, what's your first name?
Dave.
Huh?
Dave.
Dave?
Yeah.
Okay, so we say, Dave, take the ambient temperature. Dave said it was 92 because he heard the weatherman say it was 92, right? So we say, Dave, take the temperature. So he does this, and about 2 minutes later, he looks at it and says, holy cow, 117? Man, is it hot? What happened? Radiant heat. The sun does not heat the air, but it heats the object. Learn this part of the business, because when we ask you to take an ambient reading, and this is a question on a CM test, we shade a thermometer. The air down here is 92 degrees. In the sun, it's a whole lot hotter, okay? And that's why the shade of a tree feels that way to us. And isn't it true that sometimes if it's 92 degrees, or maybe 102, huh? And we get 102 around here. Have you ever heard the term, we can fry an egg on a sidewalk? Yeah, that's why the sidewalk is picking up BTUs from the radiant heat. Or you take a nice dark surface of an automobile, dark green or something. It gets very hot. It absorbs all the heat, and it's the radiant heat. But the air is not that hot, okay? All right, let's go on. Again, at this point here, questions? What do you think? Are you following this so far? Okay, it's going to get better. We're getting to the good stuff. Now, okay, here we go. Look at this chart. Boy, have I got things to show you on this chart. This chart takes at least 20 minutes. And probably after the chart, a little bit after the chart, we will take a break. Ladies and gentlemen, this is a chart that is used in a lot of textbooks. It's a similar chart. And I'm going to tell you this, if you can understand this chart right now that we go through, you will understand how refrigerant gases work. You'll understand how high efficiency furnaces work. And you'll understand why air conditioners may not work, just by understanding this chart. Because you see, what we're doing is we're starting off with a Fahrenheit temperature. So we go all the way from 0 to 250. And we actually have a pound of ice. If we add BTUs, a quantity of heat, to the ice, it's going to melt into water. And then we can warm it up and go from water to steam. And that's all we're doing. We're warming up a pint of ice and turning it into steam. And it takes a quantities of BTUs to do this. Okay? On the bottom are the BTUs. This is a very simple chart, but again, we'll talk about it as we go through, because It says here latent heat. It's called the hidden heat because we can't feel it. It says it's heat which causes a change of state with no change in temperature. Goes from ice to water or water to steam. Look at that. Causes a change of state with no change. So we got latent heat of fusion, latent heat of vaporization. As we do this, keep in mind, we're going to warm it up. We're going to add BTUs. But keep in mind that we can also do the reverse. We can refrigerate. So if we can add BTUs and cause something to happen, we can remove BTUs by refrigerating it, and then the opposite happens. That's the basics of refrigeration. Here we go. If I take a pound of ice, watch now, go from 0 degrees and warm it up to 32 degrees water. What's the specific heat of water? What's the specific heat of water is? 1. Specific heat of ice was? 0.5. So if I go from a pound of ice from 0 to 32 degrees, that's 32 degrees. How many BTUs did it take for me to do that? 16. Because the specific heat of ice is 0.5. So I had to add the equivalent of burning 16 wood kitchen matches to make the pound of ice from 0 to 32 degrees. Isn't it still ice? Sure. Here we go. Are you getting ready in that? Okay, here we go. So if I go from 32 degrees, and if I warm it up, and if I go from a pound of 32 degrees ice and warm it all the way up, warm it up to 32 degrees water. How many BTUs did it take to do that? And the answer is 144. Wow. 144 BTUs to change the state. No change in temperature. Isn't it possible that if I remove 144 BTUs from a pound of ice, I can still may have a pound of ice, I'm sorry, from a pound of water at 32 degrees, I could end up with a pound of ice at 32 degrees?
Yes.
Do you drink beer or pop, Annette? No, okay, but Annette wants to answer. Okay, Annette says she drinks pop, because I was waiting, remember I said Annette, you got to pick somebody. Anyhow, Annette drinks pop. Do you ever buy a 12-pack of pop?
Yeah.
Sure. Watch now. Heat moves from warmer to cooler. Annette, can you go to the grocery store and take a 12-pack of pop off the shelf and bring it home and put it in a cooler with 2 pints of ice? What temperature would that pop be from the shelf? About?
Depends on the room.
Room temperature. Yeah,
Yeah.
that's all. So how much you think about? About 70. So isn't it possible then that Annette could go to the grocery store, pick up a 12-pack of pop at 70 degrees, stick it in the cooler with 2 pints of ice? What do you think will happen to that ice maybe after, I don't know, 10 hours? Yeah, it ain't ice anymore, is it? It's water. What happens to the 12-pack of pop? It's cool. Yeah, and the point is, it depends on the quantity of ice and how warm it was and so forth. However, but just as the example, we would end up with 2 pints of water. Heat moves from hot to cold. The pop gave up 2 times 144. How much is that? 288? So the pop gave up 288 BTUs because the heat moves from hot to cold and it melted the ice, from ice to water. The pop gave up, watch now, think about the cold beers that we've had in coolers. But for every pint of water, the pop gave up. For every pint, it gave up 144 BTUs, but there were 2 pints in there. The pop gave up the equivalent of burning 288. Sorry, yeah, my math doesn't work, so you got to help me. But the pop gave up the equivalent of burning 288 wood kitchen matches worth of heat. Now that's become significant. See? As simple as that sounds, but you got to understand this. You got to understand this in order to understand this. Here we go. Are you ready in that now? Okay. Let's take a pound of water. This is 1 pound now at 32 degrees, and let's warm it all the way up to 212 degrees. Can we have 212 degrees water?
Yeah.
Yeah. And the specific heat of water is? 1. How many BTUs, okay, and that, oh, no, wait, I'm not ready yet. How many BTUs did it take to go from 32 degrees water to 212? How many BTUs did it take? 180, because it's 180 degrees. So it took 180 BTUs to warm up a pint of water from 32 degrees to go all the way up to 212 degrees. Is that correct?
Yes.
Keep an eye on me because I get my numbers mixed up and you got to say, hey, no, you didn't do that right, okay? So here we go now. Pint of water at 212 degrees. Let's warm it up to steam. What's the temperature of steam on a boiling stove? On a boiling pot of water on a stove? Yeah, 212. And the water temperature is? 212. How about if I turn the gas up, make a bigger fire? What's the temperature of the steam now?
212.
Still 212. Basics that we learned in high school, right? And that's all this is saying. How many BTUs does it take to change the state from 212 degrees water? You better understand this one now. From 212 degrees water to 212 degrees steam. How many BTUs did it take? It's almost 1,000. Takes the equivalent of burning almost 1,000 wood kitchen matches to convert a pound of water to a pound of steam. Now, I'm leading you somewhere. Pay attention now. No change in temperature. We went from liquid to vapor. Is it true that I can now go from vapor to liquid by removing a quantity of heat?
Yes.
Oh, by the way, can I get that temperature of the steam hotter? Sure. How can I go above 212 degrees? How? Say that again?
Add pressure.
Yeah, but we just said, if I turn up the stove and have bigger fire, the water's still 212. And the steam is still 212. How can I get the steam hotter?
Pressurize it.
Pressurize it. Pressure cookers. Are you ready now? Now, this is all got to fall into place right now. In this business, ladies and gentlemen, the word boil. Are we boiling here?
Yeah.
The word boil simply means change of state. Right, evaporating. That's all it means. It doesn't mean hot temperature. We know it as hot temperature because of what we live in. But when we teach you about refrigerant gases, it means something totally different. But all it means is change of state. Liquid to vapor. While it's doing it, it absorbs a lot of BTUs. But there's refrigerant gases that do not have to be 212 degrees. They will boil at lower temperatures. Now here's the question. And now you're going to learn right now, in the next 5 minutes, why some air conditioners don't work and how your high-efficiency furnaces, that one, does work. It's because of this chart. Here's the question. If I went from vapor and removed BTUs from the vapor, how many BTUs do I have to remove from a pound of vapor to get water? Almost 1,000. So 970, right? If I remove, and the word is, doesn't have to be steam, vapor. If I can remove 970 BTUs per pint, I can end up with a pint of water. Now we call it, so this is late, if we go this way, it's latent heat of vaporization. Watch now. If I go this way and remove BTUs, it's latent heat of condensation. Now I'm condensing, see? Now I got vapor and condense it into water, or if I heat it up, I got water and evaporate it into vapor. Is that clear? You gotta know that. Now here we go. I'm telling you, you've gotta know this part. What's in this air right here?
Moisture.
And
There.
air, gas, and gas is what? Oxygen and nitrogen. 20% oxygen, 80% nitrogen, vapor, because it's humid, you know, you run around, you sweat and all this, and there's humidity, right? Isn't that vapor?
Yes.
How hot is the vapor in this room right now?
68.
Yeah, so the vapor is not 212. The vapor in this room is 70 degrees. It's not saturated, because if it was 100% relative humidity in here, the air would be saturated and it could not hold anymore. What would be happening in here right now if it was 100 degrees relative humidity at 70 degrees? What would be happening? It would be raining, right? But the point is, we have a certain amount of gas in here, vapor. Watch. Heat moves from hot to cold. We said before, what was your name again?
Scott.
Scott. Scott has got a 30,000 BTU air conditioner. Average size house. On a hot day, hotter than 92, 100 degrees, his air conditioner should never shut off. Should just run constantly. And then it's sized correctly. So if it's 100 degrees, it'll almost not shut off. Very humid outside. Watch. Inside the house, inside Scott's house, he's got hot and humid air coming through, and it goes through the cold coil. The air gives up the BTUs. What happens to the condensation, or to the vapor that's in the air? Doesn't it condense on the coil? Right? Now watch. If it condenses on the coil, it turns into water. We got water that goes down the drain. Here you go. On a 100-degree day, Scott, hot, relative humidity, maybe you just turned it on, it's got to run a whole day to get rid of the humidity in the house. Remember, in the house, Scott comes home, it's 100 degrees outside, his house is 100 degrees, full of relative humidity. Humidity in the couch, in the clothes in the closet, on the drapes, the carpet, everything is full of humidity. We got to dry it out before the air conditioner even has a chance to start cooling properly. But even after his house is cool, there's still a lot of humidity. 100 degrees outside. How many pints of water are going down your drain, Scott? Let's say in one day, 24 hours. You just turned it on, 100 degrees in the house. Watch now. How many pints of water in one whole day, while it's running constantly, cooling down and dehumidifying, how many pints of water go down your drain in a day? You haven't got a clue? That's right. He doesn't know. Because it ain't pints. It's gallons. It pours down the drain. As the water, this is how air conditioners work. As the air comes through, it gives up the BTUs, cools the air, maybe, but it condenses the vapor. And the point is this. For every pint of water that goes down the drain, the air conditioner had to remove from the vapor that went through the coil for every pint 970 BTUs per pint. Exactly. That's almost the equivalent of 1,000 wood kitchen matches worth of heat. Watch. And it don't change the temperature. And that's the clue. Latent heat of condensation does not drop the sensible heat. It only is a dehumidifier. And the point is, if Scott's air conditioner was not big enough to handle the humidity and the sensible heat, he would have an excellent dehumidifier for his house. And if it was too small. So if it's 100 degrees outside, his house might get down to 92, and he'd be nice and dry, like Arizona, inside of his house. But he don't want 92, he wants cooler than that. So you have to size an air conditioner not only to handle the sensible heat, but the humidity, because that is the total heat load. The total heat load for air conditioning is latent and sensible heat. The air conditioner must handle both, and that's all figured into the charts. Now you understand why an air conditioner might not work on a hot day, and it's pouring water down like crazy, because it ain't big enough. Okay? You must understand this in order to understand this. This is how a condensing furnace works. Very briefly, because this is air conditioning class. We used to take a furnace and have a 400-degree stack, and all the heat went up the chimney. Now look what we got. Right, in, out. This is the exhaust. Got body temperature now, 100 degrees. And so we use plastic for a vent. All the rest of the heat that used to go up the chimney, we heat the house with. But what goes down the drain on a condensing furnace? Water. And on a 20 below zero day, the furnace is running all the time, it's the same question. Gee, how many pints of water go down your drain in a 24-hour period? I don't know, because it's gallons. It's the same thing. Products of combustion, ladies and gentlemen, is CO2 and H2O. You take gas, make fire, oxygen, you get CO2 and H2O. So if we have H2O, that's water. If I can cool the water vapor down, it turns to water. It turns from gas to liquid. And for every pint of water that goes down the drain from the condensing furnace, you have picked up 970 BTUs and put it into your house. That's how a condensing furnace works. That's why we have water. But it's still the basics. Vapor to liquid, and of course the opposite and so forth. Is it making sense now? That's what this business is built on. And unless you know that, you're not able to size things correctly. Yes, question?
On the opposite end of, like you're saying, with too small of an air conditioner, it dehumidifies well.
Yes.
And if it's too big, I was my understanding that it cools it, but it doesn't dehumidify.
Yes, excellent question. Thank you for asking that, because the other side of the coin is what could very easily happen. An oversized air conditioner on a 100-degree day again, it will cool so rapidly. It's an excellent air conditioner, excellent cooler, but it cools so quickly, it shuts off. It's supposed to be running 100% of the time on a 100-degree day. Yeah. But if it shuts off, because maybe it's big enough to cool the house if it was 150 outside. You see what I'm saying? So if it cools off, it cannot dehumidify then. But while it's running, it's still dehumidifying, and that is a very common problem. The customer doesn't complain that it's not cool enough. They complain that it's too cold and clammy in the house. See? Okay? Questions? This is a tough chart. But you have to understand it. Generally, it takes me an hour and a half to go through that chart when I'm teaching a regular semester course, because we go into a lot of other details. But I just gave you all of the basics with it. So I got two more things to cover, and then we're going to take a break. We said before that we could get vapor hotter, and the vapor could be hotter than 212, and we said that we could do that by pressurizing it. And remember, the word boil simply means to go from liquid to vapor. Doesn't vapor take up more space than liquid? Why do you think there's a pressure cap on the radiator of your car? Your car could be 240 degrees. The water could get up to that temperature. And we don't want it to boil, because if it boils, the radiator isn't big enough to hold the vapor. And plus, we can't circulate vapor, we can only circulate water. So we pressurize it, and so we increase the boiling temperature, and it does not boil. So if it gets up to 230 or 240 degrees, actually the temperature, the boiling temperature, this line here would end up coming up here too. But then when it finally does boil, the vapor then is, of course, hotter. And we can continue adding heat to vapor simply by pressurizing it. Okay? We're going to do one more. Are you ready? Because I have a question for the next person. But you're going to surprise this person, because that person doesn't know you're going to call on. By the way, you can call on somebody twice and 3 times and 4 times if you like. But otherwise, somebody different than what you've been doing, okay? Because here's the surprise for you. This person, we have a challenge for you, because during break, and we're going to have a break now in just a little bit, we have a question. We're going to ask this person after break, because you got to think about it, because if you don't have the answer, you got to talk to somebody and get an answer. The question that we have for you is, do you know how to make a soft-boiled egg? Who's going to think about that question during break? Annette? Your choice.
No.
Okay, that's your name. That's your choice. What's your first name? Rob, is it?
Yeah.
Rob. After break, Rob will tell us exactly how to make a soft-boiled egg. Now, ladies and gentlemen, we got a lot of material. I'd like you to look at the clock, and I'm really only going to give you like about a 9-minute break, and that's it. We have to start on time, okay?